first of all, what is the value of this e of x minus a whole squared for some arbitrary a, some real a? If somebody asks you this, note that if I already have a parenthesis, I can skip the outer parenthesis, right? This means it is e of x minus a whole squared. This is my g of x. Assume that, right, it's finite, it exists and so on. Let's not right now scratch our head. So for some a and right, any arbitrary an arbitrary x for whom, right, for which let's say e x squared exists. This is the only condition I want. If e of x squared exists, this almost surely will exist if a is finite, right? There is no issue there. Okay. So if I want to simplify this, why am I why am I justified in expanding that function there? Because x is after all always a real number. It may be a random variable, but it's a real random variable, right? So it's always a real number. So this is identical to e of what? X squared minus 2ax plus a squared. You can use ordinary algebra to simplify expressions involving random variables, and we are going to do that heavily from now on, because for every real value taken by x, this identity is valid. So there is no way that this cannot hold. Now we use a linearity property of the E operator. So what happens to this? Which is just nothing but a squared. So I can drop this e. A squared is some constant as far as the expectation is concerned. So its expected value is a squared itself. So as we saw yesterday, right? So this is a special case of e of ax plus b, which is aex plus b. Whatever yesterday, if I didn't say it, you can write it down also. E of ax plus b is aex plus b. The same thing applied here. Remember, if e of x squared exists, e of x will also exist. That is another property which we have not formally proved, but if a higher power exists, the lower power has to exist, because in general x squared is sitting on top of x for large values, right? You have what is called bounded convergence and all that, right? If this is if any integral or sum involving this converges, any integral or sum involving this also has to converge. There is a dominated convergence theorem. That is what it is, right? If you want to know more of the maths, you can go look at that, right? Or what we call dominated convergence, right? So I have this. So what do I want to do with this? I want to pick the a which minimizes this quantity, and I assume I can make incremental changes in a. That is, a is completely under my control. I have the whole field of reals to choose the value of a, but I want to find that a which minimizes this. A is in a sense an estimate of x which minimizes this mean squared value, or special mean squared value. It is not just e of x squared, but it is e of x minus a the whole squared. So we want to choose a what do we do? You differentiate with respect to a, very simple. So implies what? So we get a star. There is a unique minimizer which we write as a star and not as a, right? Do you or do you not get this? This does not depend on a. No matter how fancy it is, it does not depend on a at all. So it will go away. The only thing that depends on a is this part. Remember, you are right. This is a mere number as far as a is concerned. By changing a, you do not change this. So this is the significance of the mean. Basically this is equal to mx. So if somebody asks you in an interview, viva question, what is the significance of the mean, what will you say? One among many other things, it is that number which minimizes it's the best in the absence of any other information about x. The mean value is the one that is plumb in the middle in the sense of minimizing this quantity. It is that value from which the distance, the average distance to all other values taken by x is the minimum, weighted by the probability of course. So this significance of the mean itself is missed. Then what is that minimum value? This may be the minimizer, but if you substitute x equal to a star equal to mx in here, what do you get? You get what is called the variance, the minimum of this. The minimum over a of e of x minus a whole squared is, and it's unique, right? It's a global minimum. So this is a global minimum, remember. Why is it a global minimum? Because what kind of a function is this with respect to a? It's a parabola. Every parabola, right, if it doesn't has a low, I mean it's it's a proper parabola in the sense that it's, or what do you call it, concave, I mean we don't use the word concave, it's a convex U parabola, it's not the parabola which is the other way around, right. So it has a minimum and not a maximum, in other words, right. So this is a global minimum, and it is achieved at a star, which is m, and the minimum over a of e of x minus a whole squared is basically e of x minus mx whole squared. This is so important that it is written as sigma x squared, called variance of x. It is by far more important than e of x squared itself. Although e of x squared is needed to understand where it comes from. And if I want to simplify that, all I am doing is as of now I have just simply substituted a star or mx for a. But I can simplify. What happens if we simplify this? Basically e of x squared, I am going to substitute in place of a, what am I going to write? I am going to write e of x itself. What do I get if I substitute e of x here? So this is a neat formula for the variance in terms of just the mean squared value and the mean. You don't have to do a long calculation like this, you can just simply remember this. And not only that, the variance is written with squared for a reason. The variance can never be negative, it always has to be non-negative. Why does it always have to be non-negative? This quantity is a g of x which is always non-negative. Remember what we said yesterday, the expected value of a non-negative function is always non-negative. E of x squared, I pointed out yesterday, has to be non-negative. Similarly, the variance also has to be non-negative. Right? And why the squared? Because in statistics they also have a separate use for sigma x by itself, which is this positive square root of the variance. They call it the standard deviation. We are not going to use that much here in this course. It's enough if we stick to the variance, but in some equations you may see sigma x coming by itself, like for example in the Gaussian case we are going to do that today and conclude, right. you see the sigma x by if you see it by itself, you remember it's a square root of the variance. You don't have to remember the other term associated with it, right. Just remember variance, and variance is exactly this. You don't know square root involved. Okay, that is why in the for the Gaussian case it turns out, right, in the Gaussian case, right, as we said the other day long back, right, the m parameter does not affect the spread. So it turns out that the variance, a lot of things about the variance, but anyway, so I claim that it is enough for me to look at to calculate the for the Gaussian case, it's enough to look at 0 sigma squared, because it turns out that we will justify this in a little bit, but let me just at least do the 0 sigma squared, and then later on I can justify what I just now said. So now note that I am just writing sigma squared here, I am not putting sigma x squared, right. As of now I have no proof that, right, this is in fact the variance, but that is what it is going to come out to be, right. So we know that for this E of x is certainly m, this we know, that is mx is equal to m, this parameter m, because of point of symmetry, right, and as I said there is no problem with the existence of variance, I mean the mean or the mean squared. Now for the variance I am going to take m equal to 0, because it turns out that, so i.e. if I take x is 0 sigma squared, this implies that mx is 0. This is in fact this is called, this is example of 0 mean. So you can have a great many situations where the mean is 0. In this particular case you have a symmetric PDF about, which says PDF in the 0 sigma squared case, it is symmetric about the origin, and therefore the mean is 0. Mean exists, it has to be 0. In the uniform case that we talked about earlier, that a plus b by 2, I can again have mean 0 if I take what? If I take b equal to minus a, and then once again it becomes symmetric about 0 instead of something else. Okay, so I am just saying that for this case it is easier now to deal with the E of x squared for this. So it turns out that if I take 0 sigma squared, E of x squared is an integral like this, minus infinity to infinity x squared e power minus x squared by 2 sigma squared dx, and of course there is a square root of sigma 2 root 2 pi here. The difference is the x squared term here that in the so once again you integrate by parts. Integrate by parts by taking just x into x something. So if you integrate this by parts, maybe I should do it here. Just one step. So I am going to look at the integral for E of x squared. This is not, right, this is not the variance or anything, I can just simply finding E of x squared, that is all. Okay. So I have E of x squared equal to integral minus infinity to infinity x squared x by sigma 2 root 2 pi x of minus x squared by 2 sigma squared. So this I will write as x into x, okay, and I will write this as x times the integral of the remaining part is, it turns out, of course I will also do one thing. Let me pull out this 1 by sigma root 2 pi outside, okay. So it is x times minus sigma squared, this is the antiderivative of what? This is the antiderivative of x into this, okay. There is a minus sign here because there is a minus sign here, and it becomes plus integral minus infinity to infinity of the derivative of this, which is dx, right, uv minus v du, this is my v, dx into sigma squared into x power minus x squared by 2 sigma squared, right. and this is evaluated between minus infinity and infinity. Actually we are sweeping some details under the carpet here because these are all infinite integrals and so on, but what do you think happens to this first term? It will be 0 at both ends, because as I said earlier, this e power minus x squared is very strong and x power k has no effect on, if you take limit as x tends to infinity of x power k, e power minus x squared is 0. So, and what is this? This is basically back to a Gaussian integral, is it not? If you remove this a sigma squared, pull it outside, what is the rest of it? This whole thing is 0, so this is 1 by sigma root 2 pi into that thing is sigma squared times, it turns out it is sigma squared into it will be root 2 pi into sigma or something, be exactly this, or rather this thing taken here, the integral is 1 without the sigma square. So the answer is sigma squared. So what have we got here? We have got the fact that E of x squared is sigma squared and the mean is 0, right? So what is the variance? Sigma squared. So it turns out for this case that E of x, I will write it this way, sigma x squared equals E of x squared equals sigma squared. So the parameter sigma squared directly becomes the variance because the mean is 0. So why do I claim that for any m sigma squared is a variance? Because basically it turns out m, the only thing that m does is shift it right and left, and it turns out that the variance is directly the spread parameter of the PDF. So you can actually do, I'm not going to take it any further because it's very boring to take it any further, I mean this particular example, but for the general Gaussian case also, right, it turns out m is the mean and sigma squared is the variance. We have proved it for the 0 sigma squared case. M sigma squared case also exactly the same thing happens, and I have already talked about the effect of sigma squared on the shape of the PDF, right, that we talked about long back. Now you can understand where that shape is coming from. So the variance basically tells you the spread of the PDF in general, not just for Gaussian. If you look at the exponential distribution, for example, the variance will be 1 by lambda squared. It's 2 by lambda squared minus 1 by lambda squared from the mean. So the variance will be 1 by lambda squared, it's half of E of x squared. Again, lambda controls the spread, the smaller the lambda, the more the spread. For the geometric case, the variance will be 2 by p squared, or wait a minute, maybe not, so no, so it's 1 minus p by p squared, sorry, what am I saying? Anyway, okay, let's not, I'm going to end the lecture here, but just note that all these results are perfectly, are very standard. There are big tables of this. I am sure you can find all kinds of online resources to help you out. So the aim of these lectures should not be to replicate all the stuff that we have seen on the net, right, we can get elsewhere. So instead we will look only at the conceptual meaning of what we are trying to calculate, especially this kind of stuff.